down here. So no more questions for 3.2. I should put on there. 3.2, got two of them, and we'll jump to 3.3. So number 33, something that we didn't cover completely, right? We didn't do the negative in front yet. Got this little guy to deal with. It is a base of 3. And so the question is, how do we graph this guy? So the one that we know how to graph already is this little guy right here, just log base 3 of x. We should know how to graph that one. We need 3 points. First one is going to come at 1, 0. The next one's going to come at 3, 1, because that's the whole point of logs, right? Log is what exponent do you put on 3, right, to give you a 3. And it's going to be 1. And then the other one is 1/3. Oh, it escaped me here. This one's going to be 1/3, comma -1. So those are your 3 points. That's just to start off, and that's just log base 3 of x. So now we've got to go back to our transformations. Remember those transformations? So this little negative in front, that means we take the reflection about the x-axis. That's a negative. That's what a negative does in front of a log. If the number was inside the log, that means we would have. Say again.
You said if the number was inside the log.
Oh, sorry. If it was like this right here, if it had a little parenthesis, we would move this guy to the left 2 units. We're good? Yeah. But because there's no parenthesis, it's almost like this. The x is inside there, and the 2 is on the outside. So there's our transformations. That's the stuff we got to move. So first things first is let's do the reflection. And I'm going to do it a different color. So reflection, the first one's going to be, I'm going to jump this guy to here. This is going to be 1/3, comma +1. 1, 0 still stays at the same spot. Now this guy comes down to 3, comma -1. Are we good there so far? So now this is called a decay curve because it slides down like a slide. All right, I got the reflection done, chink chink, and now shift it up 2 units. Let's go with it here. So I'm gonna go 1, 2, higher, and maybe I should change pen color again. So now here's my final one. Boom, this is gonna be 1/3 still, but now it's at 3 because I moved up the y value by 2. This little guy here now is changed to 1, 2. This guy is now 1, 2. And this guy now has 1, 2. Hey, back to the original spot here. 3, 1. So there's my line. Have I moved horizontally? Okay, so I still have a vertical asymptote, comes down straight at, shifting a little over the side, but just so you can see it there. But there it is. There's my graph. Final graph is, it goes like this. Does it eventually keeps on going further and further down because these guys go down forever, or they go up forever. It's just that vertical asymptote that stops them. All right, cool with that. And 37, did you guys struggle with 37? Because we didn't do a divider either here. I wanted you guys to play with it just for a little bit here. Okay, we're good with 33? Jam in 37? Log base, oh, there is no specified base on this guy. So it is base 10, are we good there? Base 10 for this one. So let's at least graph this for our first one here. Start off with purple today. Boom, I got this one at 1, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going all the way up to 10, 1, because that's my base. And then going the other way, it's going to be at 1, 1/10 comma -1. There's my, it is really, it comes up very quickly and it just spits it out to the left very quickly here, or to the right very quickly. Okay, so now the question is, what happens if I have a 1/5 there? And so let's see. Normally what we do is we do this here, right? Let's kind of just play with it just for a second here. So normally if this is the case right here, right? You'd have a 1 here. And then the question comes up is, what exponent do you put on 10 to give you a 1? And that becomes a 0. Are we good? So now notice, to get that 1 here, the question becomes, let's see, a 1, right? How to say this? Well, yeah, the question really then becomes this: what do I put in for x right here? So that'll, it'll give me a 1 there, so I can put it, so I can put a 0 right over here. If that makes sense. You got to put a 5 there, right? Because 5 would make a 5, and then that would eventually give you that 1 that you need, right? So that little 1, 0 now, let's change pen color. It's going to be 1, 2, 3, 4, 5. Now it just became 5, 0. We're good? So just like if I write this, notice this is going to be a shifting to the left 3 units. We're good there? It always goes the other way that you think, right? It's a shifting to the left as opposed to the right. With the division here, it's a multiplier by 5 of all your x's. We're good? Because it takes 5 times more to get back to the original one that you had initially. And so in this case, you're going to put in, this guy got multiplied by 5 to get you 5, 0. This guy gets multiplied by 5, even though it's only 1/2. So now we're at 1/2 comma -1. Ooh, and then this one's no fun. This one I can't even graph. I don't want to graph that one. That's at 50, 1. If you want to put a dot all the way out there, you can, but it's 50, 1 is your dot. So here it is. It almost like stretches it out away from the y-axis. That's what's happening here. Tristan?
Is that 1/2 common negative?
Yes, Boom. So then I have like this. I have a graph that's going up. It peels away from the x, from the y-axis earlier. Boom, and it's gonna go that way. All right. And don't forget these guys here, still putting in the vertical asymptotes. Go, Dylan.
So whenever you have a fraction, you just basically get the fraction equals 0, and then from there you just solve it, basically.
Say that again, just make sure I understand you.
Like, so what we did here is we got the fraction to equal 0, and we got our first point, and then we just figured out that it's the multiplier of 5 for every single one.
Yeah, so your divider becomes your multiplier in our graph.
And it's just as it will always be like that for all the graphs.
Absolutely. Just like over here, your addition will be your subtraction from your graph, because you'll be subtracting away.
But what if we're given like the exponent, or like what if we're not given, or what if we're given like it's like log 4 and then the fraction? How would that be any different?
Let's see, make sure I'm getting you here. So log base 4
Yeah,
of
like just x over 5.
x over 5, So initially it would be, this little guy will change. Well, instead of 10, 0, it would have been at 4, 0 initially, or 4, 1 initially. So it would have gone to 20 then at that point,
Okay,
instead
so
of 50.
Proportional to the base then?
Yes, yeah. So that just becomes the multiplier to your x coordinates. Maybe a better way to say it. Oh, and good.
Is there a way to enter a custom base for a log on a calculator? Because it's only log base 10.
Yeah.
Is there no way to put in a base?
You know, I love it when someone comes up with a segue, and the segue is, we will learn that today. That's awesome. In fact, actually, there is no way, but we have a workaround.
Let me use the L or the I or L.
That's just magic.
So yeah, your calculator has only base 10 and it has base E. That is it. There's nothing else in the calculator besides those. Right? So now we got to figure out how to work it around. Hey,
At least for this set of homework, there wasn't really much to
Yeah,
show your work, right?
Yeah.
no, just kind of stuff like this right here if you're moving things around. Yeah. And then for like 54, 53, sorry, you were just moving things around. You're using a calculator to graph 61, 63. You were evaluating 65, 67, so not much there. And then you're graphing the other ones here. So not much, only probably work that was really shown maybe would be 7, 9, 81, where you're dropping the LNs. And then you just solve each of the sides. So not much to show. All right, let's jam. So are we good now? Thank you guys so much. I'm glad we actually covered the homework questions now. I hate for those things to linger in your minds as you've tried it already here. So I think I'm out of this one. Let me jump to this one now. I should have did it the other way here. Hold on, I'm gonna do it the other way. All right, so the guy that we're studying, how about this? John Napier, Scottish mathematician. Yep, he developed this stuff. And remember how he said, how he developed it? There is a division, kind of like a long division algorithm, but it has to do with exponents. It was all the way from the Greeks. So he just decided, you know what? I'm going to figure out this. I'm going to figure out this. I know that. I know those to be true, right? So that's a 0, that's a 1, that's a 2, but then I'm missing these pieces. And it is kind of interesting just to, you figure we're all the way in the 1500s, right? And we know we've had those things missing all this time, right? Even from the Greeks knew, because you can take, but no one just ever thought of, you know what? I wonder how I can get a 2 in there. You know, what's the exponent on 3 to get a 2? And so he just all of a sudden starts thinking that question. You know, part of this whole concept of seeing something, but seeing something differently. You know, you focus on something like, hey, I wonder what if. You know, it's the what if question. We had after World War II. Quick story. We first time we actually had to test long-range missiles. Right, shoot something, go halfway around the world and hit something, right? And so we just assumed that the Earth just spins. Duh, everybody knows the world spins. And so we programmed into the missile things saying, okay, let's go for it. So what happened was we would shoot a missile from here to here, and it would actually hit here or hit here. It would not hit where we want it to hit. It would actually just be longitudinally, just a little bit above or a little bit below. Like, what the heck? Yeah, so then it took a mathematician, not saying my discipline's awesome or anything, but it took a mathematician to figure out, you know what, hold on. Not only does the world spin, it actually wobbles just a little bit. It just this little, I forget how many degrees, like hardly any degrees, but it's enough. And so then the question is, where's the wobble? So then they had to figure out the wobble. They got to get math for that, and then eventually figured out, okay, when you plug in the coordinates, it's actually time of day you shoot the missile, because depending on time of day or time of the year, the wobble is different, right? You got to make sure that, so you had to accommodate for that. So interesting fact that you had to sort of think through that. But anyways, it was this cool concept. I wonder what if. And I think if I remember the story correctly, he was playing frisbee, or he saw frisbee fly. And it was that little wobble in the frisbee. And it was like, oh, this is right after World War II, right? So wobble in frisbee, or there was some kind of disc that was thrown in the air, and he figured that little wobble there was happening. Like, oh, okay, if something spins, there still could be a wobble. And so we went from there. Anyways, back to Napier. He's awesome. 1594. What he does is, and we recognize him, he just publishes a big book. The big book takes him 30 years to write. And all he's doing during this time is writing a big fat book. And he's putting in to the hundreds place, I believe. His book went to the hundreds place. So just 2 digits. It was, let's see, this would be like 0.86, right? Or maybe three decimal places, 0.864, right? And then you go to the next one. This one would be like a little bit after 1, so 1.142. And you'd write 1.142 and a 4 next to it, and just kept on going. And he went from base 2 all the way to base 300. He did base 300.
Is there
And
like an algorithm or a formula that he found or did he literally have to try like a bunch of different numbers?
he did it by using a old system all the way from the Greeks of how to do square roots using long division. It's kind of like long division, but you do it a little differently. And so you do it and you get that. And then you just have to do it for each one. So it makes this table of books. And so after that, the slide rule comes about. Right? And after that, we have a calculator, but it's still using the fundamental property. It's interestingly enough, guys, real quick here. Think about your calculator, right? You're like, oh, look, I punch in 2 times 2, it equals 4, right? But then you got to think about what is actually the calculator processing. That's the issue. And then you go higher end is when I punch in, which we'll do, is punch in log of 25 over log of 3. What's it actually doing? What's the programming behind it that makes that true, right? That's kind of what you're thinking about. Anyways, there's a historical note. Another thing that NUPEA developed, because remember we said that logs is really just multiplication, right? Check this out. This is kind of cool. It's called NUPEA's bones. So he sketched it on a bone here, and this is the newer version of it here. So dun, 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 dun. Oh, sorry, 1 second. Hey, there it is.
In this video, I'm going to show you how to multiply using Napier's bones. You'll love this, it's so easy. I'm not going to use square roots today, so I'll leave the square roots bone to the side. I'm going to multiply 6,473 by 8. Now we'll take the bones out. We need a 6, and then a 4, a 7, and a 3. So we need a 4, a 7, and a 3. And all we need to do now is take our answer grid, and we're multiplying by 8. So we put it on at 8. And then we move down the diagonals and we get our answer. So there's only 1 in the first bit there. So you get 4 there, 2 plus 6 gives you 8, 5 plus 2 gives you 7, 8 and 3 gives you 11. So that's 1, carry 1, and we get 5. So we get 51,784.
Awesome.
Now, I'd like to show you a bit bigger so you can see exactly where it's coming. I've used different colours so it's easier to see. The 4 there gives you 4. Then the next diagonal, 2 and 6 is 8. 5 and 2 is 7. 3 and 8 is 11. 1, and carry the 10. So 1 plus 4 is 5. And our final answer, 51,784.
Okay, I'm going to stop there here. That's kind of cool. This one wanted over here. From the 8 and the 3 making 11, so you carry the 1 to the next. Usually you would write it up here. You usually write it up here and then you add them down. But yeah, isn't that nifty? Eventually it's from logs, but eventually seeing the connection is you're just really just adding the units of the next one over. Like, why didn't we, right? Everybody's walking around with their bones or their plastic pieces there. But anyway, I thought that was kind of cool. There's the application of that. That is the strangest thing.
Yeah, because I was sitting in my friend's car the other night and I started playing with the thingy and then I found the calculator and I got very excited.
That's awesome.
And it like, I was like, why? No, it was like a Honda.
Oh, yeah.
That's what happens when you're in Morro Bay.
Did they have their
11:30
phone
at
broken?
night.
Uh-huh.
Because sometimes you can phone plugs into it, there's some apps. that you
No,
have to
it's like the app, it's like an app with your car.
That's weird.
Just in case you need to multiply 32 times 48, or you go inside the store.
On the drive.
I wonder what that number is, you know?
Multiply
Total
the rate of
amusement
how
here.
much you were speeding. What's the ticket for how much it was?
Officer, are you sure you're correct? All right, so we come to Owen's question. How do you get, how do you do this? How do you go, I want base? Let's do this, a 5 of 25. You guys, what's the answer is?
42. 2.
2. You got the 42, but you got the 2 correct. Okay, so log base 5 of 20.
74.
No.
I don't
And-
know.
And so here's our little dilemma, is that people that made calculators, we could have had all the bases on the calculator. That would have been a lot of bases,
You
right?
just press log and, well, you could have just pressed log and then type in the base.
Type in, yeah, you could have done that.
Not
Yeah.
do that.
The higher end calculators, I believe, do, at least some of them do that here.
Kind of.
So what we decided to do is we decided to use the most common one, which is 10. And then we decided to put in E, which is the natural number, right? The natural log. So based upon those, we can do the other ones just by a quick calculation. And so here's your calculation. And if you want to write these one down, so 3.3, if you want to start notes here, 3.3 says property of logs. We'll do the first one here. Let's see, we've got about 15 minutes. So we'll do maybe the first or the first 2 here. There's 1, 2, 3, 4 properties, and the change of base is kind of, we can consider it as a property, we consider it as a formula, so it's kind of like in between. So let's jam. Properties of logs 3.3. And the base formulas, here it is. Oh, change of base formulas. So we have to write these down. So if you want to change from log base A, so that's the base that you have. And that's the number that you're trying to get to. We change it by saying I'm going to take the log of the base that I like now, which is base 10 or base whatever. So here's the general formula. So log base B of X divided by log base B of the previous base. How does it work out on a calculator? Here it is. Calculator works in base 10. So you're just going to press log of X divided by log of A. Good there?
Does that work?
Yeah, let's try it. Let's try it for this one here. So yeah, with your calculators, if you have them, we're gonna go like this, log. And now it's gonna be, the base is already there, right? So we're gonna use log base 10, right? So log of 20, and then we're gonna go log of 5 and see what you guys get. Oh, that's right, and I have calculators. Raise your hand if you need a calculator, if you want a calculator. 1, 2, 3, the first 3 people to raise their hand. I'm gonna give you this one here, the previous one that you had. And sorry.
Oh, I am, okay. I'm so,
Yeah.
but I'm also so heartbroken that I don't get a calculator.
The good part is it'll never
You
be
know
this
what?
bad
I want
again
you to
because
have
my
it.
first
I want you to
school
succeed in
so
life.
there's papers to work.
You know what? I'm fine living
They'll
under a
get
bus
better
stop.
over
I'm
time.
gonna actually, I wanna live in my car. I wanna be that person.
I'm sure you'll manage.
Shut up. I have more money than you do.
You're not wrong.
Okay, give me 3 decimal place accuracy. Can you give me log of 20 over log of 5?
How many decimal places? No, I will not.
3 decimal places.
1.86. Yeah, you do.
861. Okay. Hey, real quickly here, look at this. Can I change the base to whatever I like?
Yes.
Yes, Camille is right. So how about this? Can you guys do the same problem over again, but do it with ln? ln 20, ln of 5. Well, now she's wrong. Because you get,
I like those
It's the
words
same
better.
thing.
yeah, it is, because it's really just a ratio of the 2 logs. That's all it is. So it doesn't matter. You could use base 10, you could use ln. You're gonna get the same exact answer either way.
Technically, I'm winning.
So on a calculator, if you have like something in base 10 and you want to switch it to base A, you just take whatever you take base 10 of your number and then base 10 of whatever you want to switch it to.
Yes, sir. Uh-huh.
So then where does B come from in base B thing?
In the general one, you can change to any base that you like. This is the general one. Now that's almost like too general, that's not useful, right?
Okay.
Because whenever we do it, we're gonna either change it to base 10 or we're gonna change it to base E.
So we really don't even need to pay attention to the base B then?
Yeah, this is kind of like the general case. Like, okay, in generality, this is what you can do. And now more specifically, these are the two things we do.
Can we play Jeopardy again? You keep asking about the class. Because it's more fun than actually doing what they want to do.
Did you like Jeopardy or did you like bingo? Which one was your favorite, Camille?
I like Jeopardy because you have to do less work in Jeopardy than you did bingo.
Okay, got it. It's all about less work. I totally understand.
See, I did rub off on Mr. McCullough.
So let's go with it. Example 1. So we're going to rewrite these. Now this one has an X inside it, so you can't actually get the answer, right? Because you have an X. But what we want to do is we want to just be able to change forms. Like where does the X go? Where does the 3 go? Sort of thing. So got 2 ways. Can you rewrite the logarithm as a common log first and then also as a natural log afterwards here? So all yours there, and let's see how far we get. Cool. All right. So A would be log of X. We're good there. Log of 3. You wanted to? We're good there. Jamming with B. It would be ln of X over ln of 3. Now also, if you were to graph this on your calculator, you do the same as well, right? So you can't punch in log base 3 of X, but you say if graph ln base 3 of X. You're going to have to go back to these guys to do it. Okay, B is all yours, log base 7.1 of 4. And hopefully we did it already here. Didn't walk around the room to see here, but it would be log of X on top. And how about log of 7.1 on the bottom? There, and then B, log of X, oh, sorry, ln of X, ln of 7.1 on the bottom. Are we good? Bam, okay. Let me do this real quickly here. So let's talk about some stuff here. Let's do the next one. I'll just label this as product property. And let's think with me here. And since we have calculators out, let's sort of see if we can do this here. Let's try it. So I got this here. I got log base 10. Let's do base 10 because we can do it on our, and I need and I need 40. There you go. 40 would be good. Yep. What is this? Log of 40. What would that be on the calculator? 3 decimal places. Thank you. So what I want to do is I want to somehow split the 4 and the 10. We good because there's a 4 and the 10 in there? So let's do this here. If that splits into 4 times 10, good there? Would that be the same thing as log of 4 times log of 10? Check that on the calculator. Let's see what happens there. Does that give you the same answer? What does it give you?
0.606. It's right at 1.
Two.
Do that.
Huh, that's weird. Well, in fact, hold on. See the 10 there, right? That's gonna be a 1 for us anyways, right? As the 10. Strangest thing. So technically, we're just having log of 4. How did that 10 disappear? Where'd it go? And that's, so I'm missing the 1 here, right? Am I missing? Oh, look at that. I got the 0.602. I got that piece. Strangest thing. So actually, I need to add, technically from this, I need to add 1 to it, don't I? If 0.602 would have been the same as that one if I just added 1. Hold on though, instead of multiplying these guys together, how about if we do this? How about if we go log 4 plus log 10? Because that would give me the 1 here. Try that one here. Let's see, log of 4 plus log of 10.
Oh, yeah, that gives the same answer as the first one.
That gives us the same answer. Okay, so hold on, then I'm thinking this. Can you guys just put log 4 only by itself? Log 4. It's 0.602 then, right?
Yep.
So hold on, so then I'm thinking I'm discovering something. See if I can write this down. Log of 40 is the same thing as log of 4 plus log of 10.
And log of 10 will always be 1. So really, log 40 is just log 4 plus 1.
Yeah, but this little piece right here, we have to add the 1 anyways, right? We're just trying to break these guys apart. So that's weird. Hold on. So multiplication inside the log. Good, good.
Is it just because the exponent?
You talk to me. What is the exponent rule?
Like we just add exponents together.
Oh, okay. Hold on. Let's see. Remember this skill, guys? Like a to the, oh, hold on. You usually got like this. You usually got x to the a and x to the b. If you're multiplying two things together in terms of numbers, what do you do with exponents? You add the exponents together. Notice what's happening. Oh, sorry. That's true. Is that true? Aren't logs just really exponents? So I think we have ourselves. Let's try another one here. Let's see. Oh, hold on. Even break this up even more. Instead of 40, can I break it up into what? 8 times 5? Would that work? Let's try 8 times 5. So let's break this up into log of 8 plus log of 5. You get the same thing? I think we just discovered some properties here. And actually it comes from this right here. It comes from that property, right? So multiplication in terms of numbers. Let me write this here. Multiplication with numbers goes to addition with exponents. Cool. Can you write a little rule here? Let's write a rule down here. So this is the product property. It says this: log base b of, how does your, let me write it the way your book writes it. Log base a of u times v is log base a of u plus log base a of v. Are we okay there? Agreed upon that? Can we agree on that? So multiplying stuff inside, multiplying the numbers leads us adding exponents together. Because logs are exponents. Hey, what's another rule from exponents? Anybody? What's the other, what gives us subtraction? What is the rule for subtraction?
I want to say division.
Yeah.
Was it division? We're just trying to, yeah, we're going to connect the division. Yeah, I think it is. You guys see if we,
X over a and y is X minus y.
that is so cool. I think this is quotient property. Sorry, scribbling here, quotient property. It is what again? It's division. So let me do this here. How about this? X to the A over, or A to the X, A to the Y makes. You guys remember that from Algebra 1? Oh, by the way, how was Algebra 1? How was Algebra 1 for you guys? Do you guys still remember stuff from Algebra 1?
We did an algebra review chapter at the beginning of the year, and then chapter 1.
She's awesomest. That's cool. How did you guys, real quick, your show of hands, just out of curiosity, how many, I'm gonna, so this means this. So log base A of U divided by V. Right, so division between numbers gives us.
Is that a U and a V or two?
Yeah, the way the book writes it, I don't like the way the book writes it, but that's the way to do it here. So it's a U right here and a V. Good there? So division between numbers inside or in the number realm makes subtraction of exponents. And let's do one more. We'll cover these properties right now, and then on Monday we'll actually do problems with it here. So next one, something called the power property. Power property says, or let's take a look at some examples here. So let's see. Oh, that's right. Hold on. What do you guys do here when you do this and this from X? You multiply. Everybody agreed with multiplying? So how does that translate? So this is this is an exponent on the number itself. So how about log base A of U to the n power? How would you translate that into a log equivalent? So if you take powers of U, you're going to multiply the exponent. So the exponent is coming here right now, right? The exponent it's exponenting the number, right? We want that n to multiply the exponent, right? So this is take an exponent of the number, right? We want this guy to be a multiplier of the exponent. Aren't logs exponents?
Yeah.
So how about this? This little n now becomes the multiplier of the exponent. Are we good? It's a multiplier on the outside. Okay. Don't have time to go into it now. Got the properties here. We'll come back on Monday and we'll actually do the problems with it here. We'll review them over here. So we have homework, just do the change of base formula. So we can go up to, I think up to 13. So you guys can do up to 13. Yep. Cool, thank you guys so much.
Thank you,
Got full
Mr.
tours, Bye, Tristan. Bye, Dylan. How are you?